Welcome to the corner of science and sleep, where knowledge meets relaxation, and every moment is an exciting journey of discovery. Imagine yourself curling up in a blanket, soft light filtering through the window, and while your body rests, your mind is guided through the mysteries of the universe, science, and the wonders around us. If you want to both learn and relax, don't forget to hit subscribe and follow the channel so you won't miss the surprising adventures we have prepared for you until the end of the video. When we lift our eyes to the sky on a quiet night, we often see seemingly simple flight paths: a bird gliding lightly through the air, a breeze blowing across the field, or the flickering light of a distant airplane. But the truth is, every moment spent flying through the air is the result of a delicate symphony of physics, biology, and evolution. Birds, from tiny species like hummingbirds to mighty predators like eagles, all carry within their bodies a perfect mechanism to conquer gravity. Every wing, every bone, every muscle is intricately designed, balancing strength and lightness, allowing them to maintain stable and graceful flight paths. When looking at a bird gliding by, we see the beauty of nature. But behind that elegance are millions of years of evolution and complex physical principles that we are only beginning to understand. The first thing that allows birds to fly is a body structure that is light yet strong. Their skeletons are hollow inside, yet still maintain enough rigidity to withstand the force of powerful wing beats. The long wing bones, the humerus, and the radius form a sturdy framework, while also supporting the feathers, natural propellers that manipulate airflow. It is precisely these asymmetrical flight feathers that generate lift through their aerodynamic shape, curved on top and flat underneath, allowing air to flow faster above the wing, creating low pressure and lifting the bird off the ground. This principle is no different from the wings humans design on airplanes, but birds do it in a far more refined and synchronized way. But flying is not just a story of wings and feathers. Muscle strength also plays a decisive role. The large chest muscles of birds attached to the sternum allow them to generate powerful thrust when flapping down. Smaller muscles assist in raising the wings, reducing drag, and adjusting flight paths. Each bird species develops a body suited to its lifestyle. Hummingbirds, for example, can flap their wings up to 80 times per second, hovering in place as if time itself slows down. Meanwhile, eagles and hawks use long, narrow wings to glide on thermal currents, conserving energy during hunting journeys that span hundreds of kilometers. The respiratory and circulatory systems of birds are also part of the secret to soaring. Unlike mammals, birds have a one-way airflow system, ensuring a continuous supply of oxygen to maximally active muscles. Their hearts are large, their heart rates fast, and their metabolism efficient, all serving a single goal: flying high and enduringly. Vision, depth perception, and environmental sensing in the air also contribute significantly, helping birds navigate accurately, avoid obstacles, and hunt with astonishing precision. If birds are perfect flying machines, insects are the pioneering experimenters in the world of aviation. Hundreds of millions of years before birds appeared, insects ruled the sky, flying with all their beauty and wonder. Bees, butterflies, dragonflies, each species has its own way of flying, generating complex airflow and adjusting lift through mechanisms that scientists took years to replicate. Their tiny wings, beating at astonishing speeds, often create vortices and unstable vibrations, achieving efficiency far beyond their modest size. Dragonflies, with two pairs of independently functioning wings, can fly backward, hover, or even remain stationary in the air, feats that many modern technologies still strive to imitate. Butterflies, on the other hand, use large wings to absorb heat and control their wing beat rhythm, maintaining stability in flight and regulating body temperature. Astonishingly, when observing insects and birds together, we notice an endless diversity in soaring strategies. Some fly powerfully and straight, others glide gracefully and conserve energy. Some rely on muscles, others on airflow and body size. But all follow the basic laws of physics: lift, thrust, drag, combined with evolution to create creatures capable of perfect flight in their environments. Every wing beat, every loop is living proof of the combination of science and art in nature. And this diversity opens a new horizon for human imagination. Watching birds and insects, we learn how to optimize lift, manipulate airflow, and control energy. These principles later became the foundation for designing airplanes, helicopters, and other flying vehicles. Each flying species is a living experiment, an open book on physics and biology that any scientist or engineer can learn from. Thus, from tiny hummingbirds to mighty eagles, from lightly gliding insects to hawk-like moths, the sky is not just an empty space, but a stage for millions of years of evolution and applied physics. When you observe, you don't just see flight, you see the subtlety of each mechanism, the perfect coordination between structure and function, and the profound lessons that nature offers to human imagination. All of it demonstrates that soaring is not merely an action, it is art built from science, a harmony of shape, force, and motion. When observing flying animals, an obvious truth emerges. Not everyone relies on powerful muscles or feathered wings to conquer the air. In the world of mammals, gliding is a smart, energy-saving strategy, yet it requires precision and subtlety no less than the wing beats of birds or insects. Flying squirrels, cougar lemurs, and some large bats exploit a simple but effective physical principle. Gravity is a partner, not an enemy. They launch from a height, just spreading their skin like a living parachute, adjusting their bodies and tails like master pilots, converting vertical falls into optimal horizontal motion. Each glide results from the coordination of gravitational force, gliding surface area, and body tilt, a physics problem solved naturally, perfectly, and continuously adjusted according to the surrounding environment. The ability to glide offers a different perspective on survival flight strategies. In dense forests, where trees are tangled and light is limited, powered flight can be risky, energy consuming, and draw attention from predators. In contrast, gliding allows animals to move smoothly, silently, and maintain maximum vigilance. Southeast Asian flying squirrels, for example, can leap from high branches, adjusting their tails and limbs to land delicately on the next branch with almost no sound. This is not just a survival skill, but also proof that nature always finds energy-efficient solutions, a principle humans have been learning from for centuries. Gliding animals also develop highly sensitive biological sensors, allowing them to adjust body tilt and gliding surfaces in fractions of a second. They detect airflow, the distance between trees, and the slightest changes in gravity thanks to intricate neural receptors in their skin and muscles. This coordination, combined with survival instincts, creates a type of biological computer powered by the living body, where each adjustment is a perfectly executed physical and biological calculation. Observing them, one cannot help but marvel. A tiny creature manipulating complex physical principles that we have only recently grasped theoretically on paper. This brings us to another aspect of flight, the ability to adapt to changing environments. Whether insects, birds, or gliding mammals, each species must cope with wind conditions, temperature, rain, and unexpected obstacles. When a strong gust blows through, a flying squirrel can adjust its patagium, tilt its body, and even lower its head to maintain its trajectory. Bats, with flexible wing membranes, rotate their long fingers slightly, change pressure on the wing membrane, and fly through narrow forest gaps without collision. Even tiny insects exploit air vortices to glide stably, even when classical equations suggest they should not be able to stay aloft. The diversity of flight strategies also reveals lessons in evolution and survival. Some species have abandoned powered flight but still survive through skillful gliding. Penguins, for instance, convert wings into flippers for swimming, while flying squirrels use patagium to move through the forest instead of running on the ground, reducing predation risk. Each flight solution demonstrates evolution, optimizing energy and safety, while fully exploiting the inherent physical principles of the environment. Flight abilities are also closely linked to social interactions and reproduction. Adult insects live only a few hours to a few days, but within that short time, they must find mates and reproduce. Accurate flight, rapid gliding, and perfect balance determine their survival. Bats, birds, and flying squirrels also use flight skills to hunt, find food, or defend territory. Every wing beat, every gliding trajectory is part of a survival behavior chain where biology and physics intertwine. Broadly speaking, flight is an expression of natural creativity where scientific principles are applied without machinery. Bird wings, bat wings, insect wings, or the gliding skin of flying squirrels All are intelligent biological designs combining aerodynamics, mechanics, and sophisticated sensors. They teach humans lessons in design, energy optimization, and motion control, principles that modern aircraft engineers, flying robots, and drones strive to emulate. Even the unstable vortices and lift forces exploited by insects are inspiring research in microflight and nano-flying robots. Flying creatures are not only masters of the air, but also natural artists. A dragonfly gliding lightly over a pond, a flying squirrel sliding from tree to tree, or a bat spreading through the darkness using echolocation all create a symphony of motion, light, and living physics. They make us realize that flight is not merely movement, it is a subtle combination of energy, perception, reflexes, and evolution. And when you look up at the sky on a quiet night, imagine every creature, from ephemeral mayflies to mighty eagles, performing together a dance shaped by millions of years of evolution. Flight is not just the story of birds or airplanes, but the journey of every adaptive and creative creature, where physics and biology intersect, and where we can learn, marvel, and find beauty in the subtlety of nature. In the world of gliding creatures, the subtlety of movement sometimes surpasses pure strength. Each sweep through the air is the result of a perfect natural calculation where gravity, airflow, surface area, and body posture coordinate like a harmonious symphony. Seagulls are not the only case. All gliding animals harness free energy from their surroundings, turning the air into an ally rather than an enemy. As a result, they can travel long distances without expending significant effort, conserving energy for hunting, finding mates, or surviving natural storms. One of the key factors determining gliding ability is the angle and shape of the wings. Seagulls, with their wide and slender wings, tilt them precisely to exploit the wind speed differences between layers of the atmosphere. Their glides often begin by ascending into faster moving air, then descending into slower air, using an effect similar to sliding from a height to maintain speed without flapping. This technique is called dynamic soaring, where the surrounding space becomes a source of energy for movement, a form of free flight that humans would never think of without observing nature. However, things are not always favorable. Winds change, airflow is disrupted by trees or hills, and unexpected obstacles always appear. In such circumstances, the ability to react quickly becomes a survival factor. Flying squirrels, kugo lemurs, and bats have developed extremely fast neural reflexes, combined with gliding membranes or flexible wings to adjust their trajectories. A slight tilt, a tail rotation, or a subtle wing flick can turn danger into opportunity, allowing them to navigate narrow gaps or avoid colliding with branches. Even a small bird can glide down from a high branch, landing perfectly in less than a few seconds, thanks to the delicate balance between lift, thrust, and gravity. This sophistication is also evident in how animals combine sensation and physics. Neural sensors in the skin, muscles, and wing membranes allow them to detect wind direction, pressure, and spatial slope. Bats use echolocation to see their path in the dark, while flying squirrels and kugo lemurs use wind perception to adjust posture. Consequently, glides are not only the result of body shape, but also continuous interaction with the environment, where every small adjustment can produce significant effects. This is proof of the harmonious combination of biology and physics, a living computer programmed through millions of years of evolution. Another important factor is speed and trajectory. While gliding, animals take advantage of natural speed to maximize distance and reduce drag. Drag not only resists movement, but also provides feedback. As airflow collides with the body, it generates information about direction and speed, helping the animal adjust every tilt, rotation, or wing extension precisely. Seagulls, thanks to their slender bodies, can fly through strong winds without expending energy, while a flying squirrel uses its patagium to reduce drag and increase travel distance between branches. In both cases, the surrounding space becomes a supportive tool, turning gravity and wind into allies rather than enemies. Moreover, gliding strategies involve learning and adaptation techniques. Birds, bats, and flying squirrels do not glide purely by instinct. They learn to exploit air currents, choose optimal launch points, and adjust trajectories based on experience. The first flights of young birds or squirrels are often clumsy, but after a few attempts, they learn to adjust angles, speed, and lift for smooth flight. This demonstrates that flying is not merely a mechanical matter, but a continuous process of learning and fine tuning. What makes gliding magical is its simplicity and efficiency. There is no need for continuous flapping, excessive energy expenditure, or super strong muscles. Just by combining body shape, posture, gravity, wind, and neural reflexes, everything becomes perfect. Even short glides, such as those of an insect or a flying squirrel in the forest, contain a sophisticated balancing system where every air current and small movement is fully exploited. This energy efficiency allows them to survive longer, search for food, reproduce, and evade predators, even in the harshest environments. Finally, gliding is not just flight, it is an art of survival. It demonstrates the agility, creativity, and dexterity that humans can hardly replicate. Seagulls fly thousands of miles across the ocean, flying squirrels move between tall trees in dense forests, and bats glide in the dark with astonishing precision, all relying on the ability to subtly exploit lift, gravity, thrust, and drag. Each glide is proof that nature always finds efficient solutions where physical mechanisms and evolution merge into a perfect, gentle, yet powerful dance. Overall, gliding is clear evidence of the diversity and creativity of nature. It teaches us that flight does not necessarily require strength, wings, or engines. Instead, flexibility, precise calculation, and the ability to utilize the surrounding environment are the keys. From seagulls over the ocean to flying squirrels and cougar lemurs in tropical forests, all are teaching us that flight is a combination of science, art, and survival, where gravity is not an enemy but part of the intricate symphony that every gliding creature harmonizes with. Exploring how humans soar into the sky is truly a magical journey where imagination, daring, experimentation, and science gradually combine to turn the dream of flight into reality. The first steps of humans were always accompanied by risks, but at the same time, they were proofs of limitless creativity. Observing vultures gliding on thermal currents or flying squirrels leaping from tree to tree, humans realize that gliding is not a miraculous phenomenon reserved solely for nature, but a principle that can be studied, applied, and improved. Not only are the creatures capable of flight, but the sky and the air currents around us are also natural tools ready to support anyone patient and observant enough to learn. The pioneers of aviation began with simple but daring experiments. They did not have powerful engines or advanced materials. They only had ideas and courage. The first gliders were often made of wood, fabric, and thin ropes, fragile and difficult to control, yet they clearly demonstrated that ideas could overcome temporary physical limitations. Experimenters, despite being injured many times, continued to take to the air, learning to adjust wing angles, speed, and body posture, a process of learning from failure to gradually conquer the sky. The story of Otto Lilienthal is a prime example of the combination of science, observation of nature, and patience. He carefully studied how bird wings generate lift, experimenting with thousands of flights to understand how wing shape, angle of attack, and speed affected trajectory. Each landing, despite the risks, was recorded and analyzed, creating a valuable database for future generations of pilots and inventors. Thanks to Lilienthal's work, the Wright brothers and many other inventors were able to design the first successful airplanes. Humans did not stop at gliders. They also learned from natural forms of flight, thermal currents, curved wing effects, lift, and drag. Modern glider pilots, like vultures or hawks, seek columns of rising hot air formed by uneven heating of the ground by sunlight. They circle in these invisible air currents, gaining altitude without engines. Once reaching an optimal height, they can glide tens or even hundreds of kilometers, observing the landscape and skillfully controlling the glider thanks to their understanding of wind direction, air pressure, and terrain. These flights, although not as loud or dramatic as jet planes, are marvels of efficiency and subtlety. No large energy sources needed, no muscular wings, only smart design and the ability to read the surrounding space. Glider pilots learn to exploit every small change in wind, every temperature difference, and even the shape of clouds to adjust their trajectory, maintain speed, and lift. This demonstrates that flying is not only a physical challenge but also an art, where intuition and scientific knowledge merge. However, gliding is not limited to gliders or pilots. In nature, many animals have optimized gliding to survive. Flying squirrels, sugar gliders, and colugo gliders use their skin membranes as temporary wings to navigate forests, avoid predators, and conserve energy. Draco lizards extend their ribs to form wings, allowing them to glide from tree to tree, while some flat bodied snakes undulate through the air to maintain balance. Even frogs and some tropical snakes have evolved webbed limbs to increase jumping distance. These mechanisms are not perfect, but astonishingly effective considering their size, environment, and survival goals. This diversity and creativity have inspired aviation designers. From the Montgolfier brothers' first hot air balloons carrying sheep, ducks, and chickens, to the early 20th century powered machines of Santos Dumont and the Wright brothers, humans continuously learned from nature. Each generation of inventors observed gliding birds, writhing snakes, and Draco lizards adjusting flight direction, applying these principles to wing design, aircraft frames, and control techniques. Interestingly, the desire to glide has accompanied humans for millennia. From Leonardo da Vinci with his creative bird wing sketches to brave experimenters testing gliders on rooftops, every effort reflects the desire to overcome gravity, explore the sky, and understand motion. Each failure, each emergency landing became a valuable lesson, contributing to the foundation of modern aviation. Today, when observing a seagull gliding over the ocean, a flying squirrel leaping through the treetops, or a pilot maneuvering a glider atop a mountain, we realize that gliding is not just flight, but an art of efficiency, effectiveness, and harmony with the environment. It is a testament to the intelligence, patience, and creative spirit of nature and humans alike, reminding us that flying does not necessarily have to be loud or energy intensive. With knowledge, smart design, and courage, the sky is always open, waiting for those daring enough to take flight. When we look at the first Wright Flyer, it is clear that it was not just a mechanical machine, but a symbol of human imagination and perseverance. 12 seconds and 36 meters may seem brief, yet that was the moment when the fundamental principles of flight, previously existing only in theory, were applied in reality for the first time. In that instant, every force acting on the airplane, gravity, lift, thrust, and drag, became something humans could feel, adjust, and control. Gravity pulled the wings downward, but lift from the forward wings and the twin propellers countered it. The engine's thrust propelled the plane forward, while air resistance tested every design detail, every wing angle, every torque on the rotating shaft. Each passing second was a symphony of four forces, blending together with astonishing subtlety. It was no coincidence that the Wright brothers spent years studying flight mechanics without rushing to install an engine. First, they had to understand how to control the aircraft in the air, how to tilt, roll, and maintain balance. Observing gliding birds and other soaring animals, they realized that flying was not just a matter of mechanical force, but an artful coordination of design, speed, and sensitivity to the surrounding environment. Like a vulture in a thermal updraft, the Wright Flyer needed not only power to take off, but also finesse to maintain suspension, to not just ascend, but fly in the intended direction. The three-axis control system, pitch, roll, and yaw, was at the heart of this concept. Before the Wrights, many inventors focused solely on lift and thrust, neglecting the mastery of direction and balance. Without control, an airplane became an object that rose and fell unpredictably, like a ball blown by the wind. The Wright brothers devised a method of wing warping, twisting the wings slightly to control tilt, combined with a rear rudder to steer. This was not a spontaneous invention, but the result of thousands of hours of testing with unpowered gliders on the soft sands of Kitty Hawk. Every failure was meticulously recorded. Every crash taught them to adjust forces and wing angles more precisely. Once they mastered control, the next challenge was generating enough thrust to maintain forward motion. No commercial engine at the time was light and powerful enough, so they built a four-cylinder aluminum engine weighing less than 80 kilograms but producing 12 horsepower. They paired this engine with a chain-driven twin propeller system, a unique but highly effective design. The airplane could now not only take off but move as desired, controlling both speed and direction. This was a turning point. For the first time in history, humans were not just flying, but flying with control, challenging gravity rather than merely accepting it. An important point often overlooked is the relationship between lift and thrust. Lift is generated by the wings, based on Bernoulli's principle and Newton's third law. Air flowing over the wings creates lower pressure above and higher pressure below, pushing the wings upward. Simultaneously, the rotating propellers generate forward thrust, helping the airplane maintain the necessary speed to avoid imbalance. If either factor is lacking, the airplane becomes unstable or crashes. The Wrights realized that controlling lift and thrust could not be separated. They had to operate synchronously as a living system. The flight on December 17, 1903, not only proved controlled flight principles, but also marked the birth of modern aviation as an art. When Orville piloted the Wright Flyer, those moments represented the perfect fusion of mathematics, mechanics, intuition, and courage. We can imagine the small bicycle mechanic, eyes glued to the wings, feeling every gust of wind, every vibration, adjusting so the airplane did not veer off course. There were no buttons or touchscreens. All was direct interaction between body, wings, and environment. The extraordinary nature of this achievement also lies in its human and intellectual dimension. The Wright brothers were not born into luxury, nor did they have formal aeronautical education, but they understood that knowledge and experience could substitute for power and wealth. They observed, experimented, failed, and continuously learned, like natural gliding birds, using their environment to learn how to sustain and navigate in the air. This is a profound lesson. Creativity and patience surpass all material circumstances. That brief flight also sparked a revolution in understanding. Humans realized that flight was not just a myth, but a measurable, analyzable, and applicable capability. From observing the lift of bird wings and thrust from flapping to building engines and propeller systems, everything reflected a fundamental philosophy. Flight is a continuous balance between forces and control. A slight deviation could cause a crash, but perfect coordination allowed even simple airplanes to glide through the air. It was precisely the combination of scientific thinking, practical experimentation, and refined intuition that turned the Wright Flyer's dream of flight into reality. They not only decoded invisible physical forces, but also taught the world that patience, curiosity, and continuous learning could turn seemingly crazy ideas into historic milestones. Even today, when watching a modern airplane cut through the wind and land perfectly, we can still envision the two small bicycle mechanics observing every gust of wind, every wing vibration, opening the era of human flight. When we look at a modern airplane gliding through the sky, it's easy to forget that behind its sleek exterior lies a complex network of forces constantly interacting. Flight is not a static state, but a continuous journey of balancing lift, thrust, gravity, and drag. Gravity pulls the airplane downward, lift from the wings opposes it. Engine thrust propels the plane forward, while air resistance pushes back, limiting speed. Every moment, the pilot or automated system must calculate, adjust, and respond, much like a conductor directing four invisible instruments in harmony. Let's start with the fuselage, the central structure that holds everything together. The fuselage is not merely a metal tube carrying passengers or cargo. It is the skeleton supporting the control surfaces, bearing loads throughout the flight, and absorbing vibrations from the wings and engines. If the fuselage is too heavy, the wings must generate more lift, risking imbalance. If too light, the entire structure could be deformed by wind forces and vibrations. The fuselage also houses the cockpit, where the pilot interacts directly with the control surfaces, from ailerons and elevators to the rudder. Here, every movement must be delicate, precise, and based on the perception of forces and airflow, like a dancer performing on a high wire. On either side of the fuselage are the wings, the true stars of flight. They are not just elongated sheets of metal. Airplane wings are sophisticated aerodynamic systems. Air moving around the wings generates lift due to the pressure difference between the upper and lower surfaces. Curved, or airfoil, wings reduce pressure on top and increase pressure below, pushing the plane upward. But wings do more than generate lift. They house control surfaces, ailerons, and flaps, allowing the pilot to adjust tilt, direction, and speed. A seemingly small tilt of a wing is the result of complex coordination between ailerons, rudder, and flaps, changing lift on each side, directing airflow, and keeping the plane stable. When the pilot wants to increase lift at low speed, the flaps lower, increasing wing area and pulling in more air like a mini parachute opening to counter gravity. To decrease lift or accelerate, the flaps raise, reducing wing area and drag. This system transforms the airplane from a high-speed machine into a maneuverable craft capable of smooth landings. Combined with leading-edge slats, the pilot can control airflow, keeping the wings stable even at high angles of attack, preventing lift loss or a stall. But the wings do not do it all. The tail, including the horizontal and vertical stabilizers, also plays a crucial role. The horizontal stabilizer controls the nose, preventing it from pitching too high or low. The elevator attached to it allows the pilot to adjust altitude by pulling or pushing the control column, changing the nose angle. The vertical stabilizer with the rudder keeps the plane from yawing left or right, maintaining a stable flight path. When the pilot presses the pedals, the rudder deflects, directing airflow and rotating the nose. The coordination of wings, flaps, elevators, and rudder is a dynamic balancing act where forces are constantly changing, yet the result is smooth, graceful flight. What is astonishing is that all these elements rely on basic physics. As the airplane accelerates, drag increases exponentially, requiring more thrust. Lift balance gravity, but also remain flexible to allow tilting, rolling, and turning. Thrust, drag, gravity, and lift. These four elements are like four dancers constantly moving and interacting, with the pilot as the conductor keeping the rhythm. Remove one, and balance collapses. Diet. Add too much of one, and the plane becomes difficult to control. Even at the smallest scale, insects and birds use the same principles. A bee or butterfly adjusts lift by changing wing beat frequency, thrust by tilting wings, and drag by spreading or closing wings. A hawk gliding over vast skies spreads its wings to maximize lift, taking advantage of rising air currents without needing flaps or rudder. A diving bird tucks its wings to reduce drag, increase speed, and modify thrust and lift as desired. Every flying creature understands the art of force balance, regardless of the simplicity or complexity of its mechanism. With modern airplanes, the sophistication of control surfaces becomes even more evident. From high-speed jets to large commercial planes, wings, flaps, ailerons, elevators, and rudders work together to maintain balance, adjust altitude, direction, and speed. This system is not accidental. It is the result of centuries of experimentation, from the Wright brothers' crude machines to modern aircraft capable of automatic landing. Every takeoff, every glide in the sky is a testament to the balance of four forces, where physics, engineering, and intuition converge. Flying is not just moving from point A to point B. It is a continuous dialogue with the sky, where the pilot or automated system reads airflow, senses forces, and reacts at the right moment. The airplane, whether metal or composite, behaves like a living body, constantly interacting with the surrounding environment. And within that interaction, the true beauty of flight emerges. Not speed, not power, but grace, subtlety, and absolute control, where every force is considered and respected. When we think of a modern airplane, it's easy to be captivated by its sleek exterior and the propellers or engines hanging beneath the wings. But everything you see is only the tip of an intricate network where physics, engineering, and intuition converge to create perfect flight. Even when the fly-by-wire system, an electronic control system replacing traditional cables and pulleys, directs the pilot's controls to the control surfaces with millisecond precision, the basic principle remains unchanged. Four forces, lift, gravity, thrust, and drag, always govern every movement in the sky. The jet engine, the heart of a commercial or fighter aircraft, is the most vivid demonstration of Newton's laws in action. When air is drawn into the intake, compressed by fans and compressors, mixed with fuel, and ignited, a high-speed stream of hot gas is expelled out the back. This action generates a reactive force propelling the aircraft forward. Thousands, millions of times per minute, aerodynamics and thermodynamics occur like a synchronized symphony where every millisecond is calculated and considered. It is not merely brute force, but controlled, rhythmic, and precise power. Jet engines operate in a perfect cycle. Fans draw in air, compressors pressurize it, combustion chambers ignite it, and turbines spin to power the compressors. It is a self-sustaining cycle where every component is interconnected and dependent, transforming tons of metal into a living entity in the sky. The fan blades at the front of the engine, taller than a person, not only compress air but also guide airflow around the engine core, optimizing thrust and cooling the mechanism. All of this happens in milliseconds, yet the result is a massive, continuous, and stable thrust, turning speed and force into a graceful dance. The marvel is not only in ordinary speed. When approaching the speed of sound, air ahead cannot disperse fast enough and compresses into shock waves, the origin of the famous sonic boom. To overcome this challenge, engineers design afterburners, where additional fuel is injected into the hot airflow, increasing pressure and generating extra thrust. This is the art of turning a conventional jet engine into a supersonic machine, but at the cost of massive fuel consumption, extreme temperatures, and intense noise. The Concorde and Tupolev Tu-1144 exemplify the boldness of transforming physical theory into a real flying experience. They nearly have transatlantic flight time, but were accessible only to a few passengers who could afford it. While supersonic flights feel extraordinary, commercial jets represent subtlety and stability. Engines must be reliable, withstand high pressure and temperature, and operate thousands of hours continuously without failure. They are built with highly precise materials like titanium and ceramic composites, expanding with temperature without deforming. Seemingly minor details, paint layers, smooth fuselage, nose shape, all influence aerodynamics, reduce drag, and help save fuel. Here, engineering becomes art, where every detail has a purpose, and all details work in harmony to achieve perfect grace in the sky. Like birds or insects, airplanes constantly interact with the environment. Thin air, wind, pressure, temperature all affect lift and drag, requiring the pilot or automated system to make continuous adjustments. Flaps extend, elevators tilt, rudders turn, all to maintain a delicate balance between speed, lift, and gravity, ensuring the aircraft not only flies, but flies steadily and safely. A modern airplane doesn't just glide through the sky, it reads the sky, responds to it, and uses physics as a language to communicate. Supersonic speed or stable flight, the jet engine remains loyal to the basic principle: push air backward, and that action propels the plane forward. At 9,100 meters, where the air is thin and pressure low, flight systems must continuously fine-tune thrust, lift, and drag. The fly-by-wire system helps the pilot do this precisely, but the fundamental feeling remains like controlling a giant metallic bird: balanced, responsive, and graceful. And then, looking out the window, you see the jet engine roaring softly beneath the wing, but inside it is an entire world of physics dancing. Air is drawn in, compressed, ignited, and expelled thousands of times per minute. Every airflow, every pressure, every reaction becomes a graceful movement, carrying hundreds of people safely across half the globe. The airplane, from its seemingly rigid exterior, becomes a living entity, flying with rhythm, speed, and grace like a tightrope dancer. In that moment, you realize that flying is not magic, but the subtlety of science and engineering, where physics becomes a tangible, emotional experience. Jet engines, whether powerful or sophisticated, are only part of the chain of interactions between lift, drag, gravity, and thrust, the four forces shaping every journey in the sky. And it is precisely the finesse in balancing these four forces that transforms a metal tube into a giant aluminum bird, gliding through the sky with elegance and absolute power. When a helicopter lowers its rotors, preparing to land on a rooftop or a narrow mountain pass, an observer can be mesmerized by its smooth and seemingly magical agility. But behind that hovering appearance lies a complex network of mechanics and physics. The main rotor spins hundreds of times per minute, adjusting the pitch at every point in its rotation to maintain lift, while coordinating with the tail rotor or coaxial rotor system to counteract torque. Every tiny movement is calculated because even a slight deviation can destabilize the entire aircraft. The helicopter pilot, like an artist, makes thousands of micro adjustments in a few minutes to keep the aircraft steady. This creates the sensation of controlling a living creature capable of tilting, rotating, moving forward and backward, and hovering perfectly at will. Unlike jet airplanes, helicopters do not rely on forward motion to generate lift. This allows them to access places no other vehicle can reach, from cramped urban hospitals to remote mountain peaks or dense forests. This versatility makes helicopters invaluable for rescue, medical evacuation, firefighting, military transport, and even scientific surveys or adventure tourism. Each mission requires the pilot to coordinate three control systems simultaneously: the collective to adjust lift, the the cyclic to move in the desired direction, and the pedals to control the tail rotor. This coordination is a mechanical dance where brain, senses, and muscle memory must synchronize perfectly. From a technical perspective, helicopters present a harmonious combination of classical mechanics and modern technology. Newer models are equipped with fly-by-wire systems, converting the pilot's inputs into electronic signals, allowing for more precise control, reducing overreaction or human error. Some experimental models are even approaching fully autonomous or remotely operated capability, opening potential for delivery, surveillance, and rescue without a direct pilot. However, despite all advancements, the basic physics remain unchanged. Lift, drag, torque, and gravity must still be precisely balanced for safe flight. If helicopters are the artists of near-ground airspace, rockets are the warriors of the sky and beyond. They do not fly by lift or rotors, relying entirely on Newton's third law. Every action has an equal and opposite reaction. When fuel and oxidizer combust in the chamber, hot gases expand and are expelled through the nozzle, generating maximum upward thrust. This force is sufficient to overcome Earth's gravity and propel the rocket from the dense atmosphere to near vacuum in space. Unlike airplanes, rockets do not require surrounding air. They carry everything needed for combustion, including their own oxidizer. Therefore, they can operate at altitudes where the atmosphere is too thin to support burning. The rocket's fuel system and combustion chamber are a lesson in extreme energy management. Liquid fuel, liquid oxygen, nitric acid, or other oxidizers are pumped in precise ratios into the chamber, where they burn in a controlled yet explosive reaction. Hot gases exit at extremely high velocity, generating enough thrust for the rocket to overcome the gravitational barrier. This process does not last just a few seconds. Rocket engines must remain stable for minutes, even hours in the case of probes or space shuttles. Precision to the second and millimeter is critical, as even a small error can cause the rocket to veer off course or fail entirely. Rockets are also machines of patience and experimentation. Every launch is the result of thousands of hours of design, simulation, and testing. Materials must withstand extreme temperatures and pressures, fuel systems must respond instantly, and controls must automatically adjust for every fluctuation to maintain the desired trajectory. Once beyond the atmosphere, rockets become objects of pure physics. Weightlessness, no friction, only thrust, inertia, and gravity guiding their path. From helicopter rotors on rooftops to rockets crossing Earth's boundaries, all flying devices rely on the same language of physics, applied differently to achieve distinct goals. What is most captivating is how we, with all our intelligence and creativity, have built these vehicles. From the complex, vibrating machines of helicopters to the boundary-defying warriors of rockets, all bring fundamental laws to life. Newton, Bernoulli, pressure, thrust, and torque. They demonstrate that physics is not just formulas on a blackboard. It is an experience, a feeling when rotor blades cut through the air, when a rocket expels hot gases, when a helicopter hovers smoothly between wind and gravity. In the moments when a helicopter hovers, a rocket rockets skyward, or a jet glides through the clouds, an observer realizes that every flight is a ballet of forces and motion. Every airplane, helicopter, or rocket is a vivid testament to creativity, engineering, and applied physical knowledge with near-perfect precision. And as technology continues to advance with automation systems, fly-by-wire, or high-efficiency fuels, the core principle remains unchanged. Flight is the art of controlling forces, speed, and balance in three-dimensional space, and humans are the conductors of that dance. When a rocket leaves the launch pad, an observer can see a massive trail of fire and hear the roar shaking the ground. But it is the hot gases expelled at extreme velocity that truly generate motion. The flames are not the direct cause of the rocket's ascent. They are the reaction of gases expelled backward, propelling the massive machine in the opposite direction. Every moment, fuel burns violently, releasing enormous energy to counteract Earth's gravity, gradually lifting hundreds of tons of steel, fuel, and payload out of the atmosphere. Rockets are not energy-efficient machines. In fact, they are extremely inefficient compared to any other mode of transport because to achieve the goal of escaping gravity, the majority of the rocket's initial mass is fuel. A typical rocket weighs hundreds of tons at liftoff, but when it reaches orbit, only a small portion of the payload remains. Every drop of burning fuel is a moment of using raw power to achieve finesse, the required velocity, a stable trajectory, and a safe payload. Earth's gravity is the strongest adversary every rocket engineer must face. The rocket must reach escape velocity, the speed at which an object is no longer pulled back to the planet. This number is approximately 25,000 miles per hour, but they do not need to reach that speed immediately. Instead, continuous thrust combined with a carefully designed flight path, ascending vertically while following a curved trajectory, creates a balance between altitude and horizontal speed, a precise coordination of energy and trajectory. To optimize energy, most rockets are designed in stages, each stage consisting of its own engine and fuel tank. The first stage, usually the largest, helps the rocket leave the ground and penetrate the dense layers of the atmosphere. When the fuel is depleted, this stage is jettisoned to reduce weight, allowing the next stage to propel the payload higher and faster. Some missions even include a third stage to place the spacecraft into precise orbit or perform deep space missions. Shedding unnecessary components step by step is a clever use of physics, akin to climbing a mountain with an empty backpack, lighter and faster. The basic principle is simple. Push mass in one direction, and the rocket moves in the opposite direction. Whether solid fuel, liquid fuel, or ion engines, Newton's law dominates. Solid fuel engines are powerful and reliable, but cannot be shut down once ignited, while liquid fuel engines provide better control. They can start, stop, or adjust thrust in orbit, suitable for delicate maneuvers. Hybrid systems and experimental plasma or electric engines promise to revolutionize long distance space travel, though they have not yet replaced chemical rockets in the launch phase. A recent breakthrough is the reusable rocket, reducing cost and increasing the sustainability of spaceflight. Machines like SpaceX's Falcon 9 can land vertically, ready for the next launch, like tossing a pencil into the air, letting it spin a few times, and landing perfectly on an eraser. This idea demonstrates the combination of fundamental physics and modern engineering. Newton's laws remain unchanged, but technology has turned a dream into reality. Once the rocket reaches orbit, horizontal velocity dominates over vertical altitude. Low Earth orbit, LEO, is where most satellites, probes, and even space stations like the ISS operate, traveling at roughly 17,000 miles per hour, allowing them to complete a circle around Earth in just 90 minutes. Orbit is not flying in the traditional sense. It is a state of continuous free fall where an object falls around the planet, never touching the ground, because Earth curves just enough for the object to keep falling along a curved path. The balance between gravity pulling down and horizontal inertia creates an incredibly delicate cosmic performance. Circular, elliptical, polar, or sun synchronous orbits are all designed based on the same principle. Reach just enough horizontal speed to avoid falling while maintaining a trajectory suited to the mission. Every satellite, telescope, or space station is living proof of understanding and applying physics. Returning to Earth presents an entirely different challenge. During re-entry, a spacecraft encounters dense air at speeds up to 17,000 miles per hour. The air is not a soft cushion. It acts as a massive wall of fire, compressing the air in front to thousands of degrees, generating extreme heat. To survive, spacecraft use heat shields, special materials that absorb and dissipate thermal energy. Some shields ablate layer by layer, sacrificing outer material to protect the interior. The spacecraft's shape is also crucial. Rounded capsules evenly disperse heat while increasing aerodynamic drag to slow the descent. Throughout the journey, from launch to orbit and finally re-entry, every step is a fusion of physics, engineering, and human imagination. Rockets are vivid proof of power, patience, and intellect, where every second, every kilogram of fuel, every scorch mark on the heat shield is calculated to ensure success. They turn the sky from a ceiling into a gateway to space, carrying humans and robots to places that once existed only in dreams. From the blazing trail on the launch pad through the curved orbit around the planet to the violent yet safe landing, each rocket is an illustration of the pure beauty of science. Energy converted into motion, motion into orbit, and orbit into the ability for limitless exploration. This is the perfect combination of classical physics and modern engineering, where every reaction is anticipated, controlled, and harnessed to open space. the frontier where humans have never set foot, yet through imagination and technology, now feel closer than ever. Re-entry into the atmosphere is an art of absolute precision. A slight deviation in angle can have catastrophic consequences. If the spacecraft enters too steeply, temperatures can spike and incinerate the hull, and the G-forces can become dangerously high for the crew. If the spacecraft enters too shallowly, it can skip off the atmosphere like a stone bouncing on water, landing in unforeseen locations, or even failing to remain in the intended orbit. The reentry corridor is so narrow that even a small mistake can alter the entire mission's fate. Therefore, every calculation, every guidance mechanism, and every thrust adjustment must be perfectly synchronized to ensure the spacecraft enters at the correct angle and lands within the safe recovery zone. For more distant missions, such as returns from the Moon or Mars, the speed and temperature during reentry are even more extreme. A spacecraft returning from the Moon travels at around 24,000 miles per hour, meaning the atmosphere must endure tremendous compression and temperatures reaching thousands of degrees. The heat shield must be designed with extreme sophistication, often capable of dispersing and absorbing heat by self-sacrifice, with the outer layer burning away gradually to protect the interior. The shape of the spacecraft also plays a decisive role. Round, blunt capsules, such as those on Apollo or SpaceX's Crew Dragon, help distribute heat evenly while increasing drag to slow the descent. Some spacecraft deploy parachutes to descend gently into the sea or land. Others, like the Space Shuttle, glide down a runway like a powerless airplane. But engineering is not the whole story. The poetry of space travel exists in each moment. Orbiting is hovering on the delicate boundary between falling and flying, suspended in motion where there is weightlessness and distance. Re-entry is returning home through a storm of fire and gravity, decelerating, silent, until when the parachute deploys, Earth seems to rise up to welcome you. Orbit is not flying like an airplane. It is a continuous state of freefall, circling the planet without ever touching the ground, relying entirely on inertia and horizontal speed. This subtlety reminds humans of natural flight designs. Long before we sketched the first flying machines, nature had solved countless engineering problems perfectly. Hummingbirds hover midair, maple seeds spin to the ground. These were nature's first aeronautical engineers. Looking closely, one sees that each movement is optimized: lift, stability, energy efficiency. This is the inspiration for biomimicry, where scientists learn from nature to design airplanes, spacecraft, robots, and modern flying devices. The Wright brothers fundamentally copied pigeons and hawks, but today, simulations are far more sophisticated. We do not merely replicate wing shapes, but also study muscle motion, feather flexibility, and response to turbulence. Ornithopter aircraft are a prime example. Flapping robots must continuously handle lift, thrust, and stability with each beat while maintaining agility to fly through confined spaces, hover, and dive precisely. These machines are suitable for surveillance, search and rescue, or transporting sensitive materials. Nature also inspires from insects. Flexible asymmetrical wings generate lift in ways that break traditional aerodynamic patterns. Tiny aircraft mimicking bees, flies, or dragonflies can operate in tight spaces, fly through gusts, and continuously adjust to maintain stable trajectories. Some even integrate artificial muscles made from smart materials that contract or expand when electrically stimulated, simulating the precise wing beat of insects. Inspiration from nature does not stop at wings. Birds, lizards, and even butterfly scales inspire flight stability, heat resistance, noise reduction, and aerodynamic optimization. Owl feathers with serrated edges enable near-silent flight. Compound eyes of insects expand vision without distortion. Spinning seeds aid in dispersal and material transport. All are lessons in optimizing shape, velocity, and motion, lessons modern technology applies to airplanes, UAVs, and exploration robots. Even in navigation, biomimicry opens new possibilities. Migratory birds crossing continents, insects returning to nests, bats navigating dark caves all use vision, magnetic fields, and sound waves. Studying them helps develop autonomous guidance systems, allowing UAVs to navigate without GPS, applying similar principles to space or hazardous environments. Biomimicry demonstrates that nature itself is technology, honed over billions of years of evolution, refinement, adaptation, and optimization. Birds do not need jet engines, yet fly precisely. conserve energy, and continuously respond to their environment. Observing the midair spins of sparrows, the hovering of bees, or the echolocation of bats in caves teaches not only physical structure but also sensory feedback and continuous control, a crucial lesson for designing aircraft and self learning robots. Each time a robotic wing flaps, each time a spacecraft re enters safely, we witness the perfect combination of physical principles, modern engineering, and inspiration from nature. These machines do not fly by brute force, but by elegance, imagination in collaboration with nature, and the human spirit of exploration. By studying nature, from birds to insects, from seeds to fish, we realize that every perfect design combines structure, motion, and continuous response, a philosophy applicable to every machine, from spacecraft to micro aircraft, and even environmental exploration robots. From this, we learn that space travel, orbiting, or biomimicry is not merely engineering. It is a dance between science, nature, and imagination, a fusion of absolute precision and elegance, of challenge and beauty, of immutable physical laws and infinite creative solutions. It is proof that when we learn from nature, every door to the cosmos becomes closer, and the dream of flight beyond Earth ceases to be imagination and becomes a tangible possibility. Gliding is not only a survival skill, but also a magnificent symphony of biology and physics. Each species must balance weight, lift, muscles, respiratory systems, and equilibrium senses to maintain stable flight. Insects, the pioneers, invented gliding from primitive exoskeletons originally used for insulation or body protection. Millions of years of incremental progress, wings extending, supporting muscles developing, flexibility and flapping, produce tiny but extremely efficient flying creatures. Their ability to fly represents an optimally designed, energy efficient, and flexible system, allowing access to new food sources, evasion of predators, and expansion of their survival territory. When the pterosaurs appeared, the ascent of vertebrates into the sky marked a remarkable innovation. These species developed enormous wings, relying on hollow bone structures and stretched membranes between fingers, forming giant sails capable of gliding across prehistoric landscapes. This solution was entirely different from insects but shared the same goal: flight. The pterosaur structure demonstrates diversity in evolution. Facing the same survival problem, each creature devised a unique solution, optimizing flight capability through different physical principles. Birds represent the next generation, inheriting improvements from small feathered dinosaurs. Archaeopteryx, the primitive bird from about 150 million years ago, illustrates that feathers were not always for flying. Initially, feathers served for insulation or display, but evolution rapidly transformed them into flight control tools. Hollow bones, a deeply curved sternum, powerful flight muscles, efficient respiratory systems, and keen eyesight all merge to create smooth, precise, and dynamic flight mechanisms. Birds do not merely fly, they exhibit perfect balance between structure, force, and motion, capable of inhabiting areas ranging from the icy Antarctic to the Himalayan highlands. Bats, emerging about 50 million years after birds, took a different path. Their entire hand became a wing frame, with skin membranes stretched between fingers, providing extraordinary flexibility. They combine wings with sonar, a sound-based navigation system, to fly accurately in darkness. This is a unique integration of biological structure and behavior. Flexible wings enable precise movement, ultrasonic waves allow orientation in extremely low light, and bodily energy is optimized for each wing beat. Bats demonstrate that gliding is not merely a physical structure, but also continuous environmental response and real-time information processing. Importantly, whether insects, pterosaurs, birds, or bats, there is no single blueprint for flight. Each species devises its own solutions for takeoff, landing, balance, control, and aerial movement. A creature must confront basic physical questions: how to generate lift without excess weight, how to land without breaking bones, how to optimize bodily energy for long flights. Over millions of years, incremental changes, lighter bones, more efficient muscles, faster reflexes, accumulated to produce exquisitely agile, fast, and flexible flying creatures. From here, inspiration from nature transitions into modern technology. Engineers study bird, bat, and insect wings to design airplanes, UAVs, and micro-flying robots. Ornithopter aircraft replicate the rhythmic wing movements of insects, remaining flexible to fly in confined spaces. UAVs inspired by bat wings use flexible membranes to maneuver in gusty conditions. Even seeds, with their slow spiraling descent, suggest passive gliding devices for transporting sensors or medical supplies without electrical power. Nature becomes the perfect prototype, offering solutions to complex engineering problems. Notably, in the new era of aviation, biological inspiration merges with electrical technology. Electric airplanes and UAVs are gradually replacing combustion engines, reducing noise, emissions, and increasing efficiency. The basic principle mirrors nature: reduce weight, optimize energy, maintain flexibility, and precision. Electric air taxis, autonomous drones, vertically landing rockets embody lessons drawn from insects, birds, and bats applied to modern technology. They are recreations of natural gliding, but with superior technical capability: cleaner, quieter, and more efficient. From a broader perspective, both nature and technology aim toward the same goal: efficient, precise, and sustainable movement in three-dimensional space. Gliding exemplifies the power of evolution and boundless creativity. It teaches us that there is no single solution, only a subtle combination of structure, force, reflex, and environment. From dragonfly wings, pterosaurs, birds, bats, to modern UAVs and electric aircraft, flight is an art, a science, and a philosophy of life, inspiring admiration, curiosity, and the ambition to explore the infinite skies. Today, small electric aircraft have appeared in the sky, gliding gently and more quietly than any vehicle ever before. They carry one or two passengers, conduct training flights, short trips, or demonstrations, and more importantly, prove that this technology is no longer theoretical but can actually work. Even if not yet ready for long-term commercial purposes, these prototypes reveal enormous potential, reducing noise pollution, limiting emissions, and improving the flight experience. Lithium-ion battery technology and hybrid systems are continuously being improved to increase energy density, reduce weight, and enhance efficiency. Some designs combine electric motors with small fuel-powered generators to ensure safety when backup is needed, emphasizing that relentless innovation in aviation continues to coexist with the fundamental physical principles that nature has demonstrated for millions of years. Electric motors bring a magical simplicity: fewer components, easier maintenance, less wear, and quieter operation reflect a philosophy close to nature: high efficiency, minimal energy consumption, and environmentally friendly. Regional flights and short-distance travel could become the standard in the coming decades, especially as infrastructure is upgraded and green energy becomes widespread. It is a shift from flying for survival or exploration to flying for convenience, efficiency, and environmental friendliness, a logical continuation of how insects, birds, and bats have exploited the sky. But human ambition does not stop at horizontal flight. The dream of vertical flight, once achieved by helicopters, is now elevated with electric vertical takeoff and landing vehicles, EVs. They are a cross between drones and future air taxis, with sleek fuselages, multiple small distributed rotors, and smoother, safer flight. Distributed electric propulsion, rather than a single large rotor, ensures stability even if one rotor fails. A perfect example of learning from nature. Multiple organs perform the same task, increasing survival chances under risk. Dozens of companies worldwide are testing these prototypes, and very soon, air taxis could weave between skyscrapers, opening an entirely new mode of urban transportation. At the same time, drones are changing the way we view transportation and surveying. No longer limited to quadcopters for photography, they can deliver medicine and essential goods directly to homes, especially in remote or hard-to-reach areas. They are also applied in agriculture, environmental research, and emergency response, monitoring natural disasters or assessing damage that humans cannot quickly access. When integrated with artificial intelligence, drones will become key tools in many industries, from forest management to urban logistics, enabling optimal, safe, and efficient use of the skies. Higher in the sky, reusable rockets have transformed access to space from a distant dream into reality. Previously, each launch meant wasting billions of dollars as rockets fell into the ocean. Now rockets can land vertically, be refueled, and launched again, significantly reducing costs and opening possibilities for space tourism and faster, cheaper satellite deployment. Not only the wealthy, but also teachers, artists, and scientists can experience weightlessness and view Earth from low orbit. The potential for suborbital high-speed flights carrying passengers from one continent to another in less than an hour is also being seriously explored. While commercial supersonic flights are making a comeback after the Concorde era, modern technology promises smoother, more fuel efficient, and safer operations while reducing environmental impact. Other innovations, such as solar powered drones like hydrogen engines and lighter materials, are quietly reshaping aviation without altering the fundamental shape of aircraft. Satellite based air traffic control, AI assisted pilots, and advanced materials are making flights safer, more efficient, and sustainable while maintaining the sense of freedom and limitless vision. All of these advancements reflect a principle inherent in nature. Gliding is a delicate balance between force, weight, energy, and control. From the wings of ancient insects, pterosaur sails, bird feathers, bat membranes to modern electric rotors and lithium batteries, humans continue to learn from millions of years of natural experimentation. Every electric flight, every vertical takeoff, air taxi, every drone, and every reusable rocket tells a story of ambition, perseverance, and relentless creative intelligence. And despite technological changes, the sky retains its vastness, tranquility, and inspiration. We fly to explore, to move faster, to connect the world, but we also fly to experience the freedom and perspective only possible from above. Gliding from bird wings, bat wings, or electric aircraft wings reminds us that freedom, intellect, and creativity are inexhaustible forces. The sky is wide, infinite, and humble, yet it is also the source of dreams, ideas, and humanity's timeless progress. Even in the most peaceful moments, when the sun is just rising, or the sunset paints the horizon pink, the sky still invites us to look upward. A small bird weaving through the air, flapping its wings softly like the heartbeat of nature, an electric aircraft taking off, gliding lightly over the city, or a prototype rocket returning to Earth in magical silence, all remind us that flying is not merely a physical act, but an emotional and spiritual experience. We witness the seemingly impossible, objects heavier than air through human intellect and creativity, leaving the ground and reaching the sky. It is no longer novel for today's generation, yet the wonder never fades, becoming subtler and more connected to everyday life. In every flight, whether small or large, we see the interplay between nature and technology. Smooth electric aircraft, vertical takeoff air taxis weaving among skyscrapers, or drones quietly surveying fields all demonstrate intelligence inspired by nature, from the rhythmic flapping of bird wings, the flexible wings of bats, to the wings of ancient insects. Each design solves complex problems, balancing forces, reducing weight, optimizing energy, and increasing safety. But beyond the numbers and mechanics, they evoke a sense of freedom and connection to the wider world, reminding us that the sky has never been limited by human-imposed boundaries. And then, as night falls, the sky becomes a tranquil canvas of stars, where each light can tell a story. Flights, from a hummingbird gliding gently by the window to a reusable rocket soaring through the stratosphere, create a continuous rhythm between Earth and space. We pause to reflect, needing no explanation, no analysis, simply experiencing the wonder. This is the moment where science meets the soul. Understanding of physics, technology, and evolution runs parallel to admiration, amazement, and the humbling sense of the vastness around us. These experiences also open a window to imagination, where we dream, soar with ideas, and explore. Drones delivering medicine to remote areas, air taxis navigating through cities, rockets carrying humans to the edge of space, all evoke the magic of movement while reminding us that flight is the power of imagination and creativity. As our eyes follow wings, rotors, and rocket trails, we connect with a long history of effort and aspiration, from ancient dragonfly wings, pterosaur sails, bird feathers, bat membranes, to modern electric aircraft and spacecraft. And in that moment of stillness, whether gazing at the night sky or listening to birdsong at dawn, a gentle, boundless feeling fills the soul. It reminds us that flying is not merely about technique or speed, but a connection to the universe, to history, and to ourselves. Every flight, large or small, is an invitation to keep dreaming, keep imagining, and keep exploring the unknown. It is proof that, as time passes, the sky remains a place of freedom, creativity, and inexhaustible wonder.